Welcome back. This is video 4.22. We're still in chapter 4 of the text. In the last video, 4.21, we talked about the differences between many of the kinds of factor analyses. Today we're going to go through some of the tables in the text, namely 4.9, 4.10, and 4.11, and we'll also go over figure 4.11 in the text and talk about the differences in the tables there. So our first one is table 4.9. Notice this is a side-by-side summary table on how the summary statistics for the principal factor method compare with the statistics for the principal component method. So on the left we have PCA versus principal factors, or principal axis. Notice when we look at the principal component method, we have that look here at the 54% versus the principal factors. We have 18.8%, indicating that the principal component method accounts for almost 3 times as much variance with 2 factors compared to the principal factors method. And this is because the principal factors method has unusually low values of the squared multiple correlations due to the spread of the variables in that data set. However, the goal of common factor analysis, which principal factors is a common factor analysis, the goal is not about maximizing the amount of variance accounted for. The goal is to account for the correlations among the variables, and this is done by separating the unique variance for each variable from the common variance component. Now, it's assumed that the common factors are independent of the uniqueness values in the population, and the two can be used, or excuse me, the two can be considered separately. So using the factor loadings and the uniqueness values shown in the principal factor summary table here in table 4.9, the common factor model can be used to reconstruct the original correlation matrix as closely as possible, and we use an equation that's equation 4.22 as shown in the text. Now this is the equation here on the Excel doc that I have up. The R plus is the reconstructed matrix that you use the factor loadings from principal component method, and then use the transformation of that plus uniqueness values that we had in table 4.9, and I have all of those values up, and we can use that to get a reconstructed matrix. Now what I have on the Excel doc is not from the principal component method, but it's actually the principal factor method, because the book already does the calculations for the principal component method. So I'm going to do the calculations here for the principal factor method using SMCs as communalities. So I'm first going to highlight this area, and we're doing matrix multiplication. Take the factor loadings and the transpose of the factor loadings, and we're going to add that to our uniqueness matrix here. And that's what we get for the reconstructed matrix, or the reconstruction of the original correlation matrix. Next, we're going to take this reconstructed R plus matrix and subtract it from the original correlation matrix R that I have included here. So I'm going to take this and just copy it and I want to paste the values there. And we're just going to do simple subtraction this matrix minus this matrix. Now you'll notice I've highlighted two things. Make a note from the text that the largest discrepancy value was 0.096 of the residual matrix for the principal component method. And the original correlation matrix value in this cell was 0.270. And the reconstructed correlation matrix value underestimates it with a value of 0.174, and that's from the text. Now what I've just done is constructed the same kind of model according to equation 4.22, the one I have up here, for the results of the principal components analysis from table 4.9. And what I've highlighted in this residual matrix is 0.241. That is the largest discrepancy value, which is more than twice as large as the maximum discrepancy value for the principal factor analysis, which once again was 0.096. Now this should highlight something very important. The goal of common factor analysis is to account for the correlations, while the goal of PCA is to account for as much variance as possible in the observed variables. Now let me show a demonstration of that. If you recall from video 4.13, where we talked about principal components analysis, talked about having three variables. And the goal of principal components analysis was to account for all of the variance in here. Okay. Whereas the common factors method, or methods, and we're just talking about principal, I'm going to put that in parentheses here, was not the same. The goal is to account for the correlation. So we're looking at shared variance here. So obviously we're going to get different numbers if we put them into a table like we did table 4.9. And obviously there's pros and cons. For example, we just saw that the common factor structure does well in reconstructing the correlation matrix, but it would be more desirable to have more than 18.8% of the variance accounted for in the common factors part of the model. So if we go to table 4.10 in the text, we're comparing principal factor method using actual communalities to iterated principal factor method. Notice that when actual communalities from the principal component method are used in the diagonal rather than squared multiple correlations, we have 40.3% of the variance that's accounted for. For iterated principal factor method, it's kind of in between the principal factors on table 4.9 and the one to the left there. We have 28.3% of variance accounted for. Now it's important to make a note here that the low variance accounted for is not some kind of failure of the methods, but rather it's an expression of different goals for each method. In common factor condensation methods, the goal is to separate out the variance that is unique to each variable from the variance that is common to all, like I did in the previous slide. Okay, so the common factor is what's unique to each variable versus what's common. What's common to all, and in fact we can draw new diagrams if we needed for each of the different kinds of common factor analyses. So let's move on to figure 4.11, which compares these three principal factor methods with one another, and also with three additional methods. We have the maximum likelihood, alpha, and the principal component factoring. So we have 6 methods here, and they're compared in 3 ways. We're looking at percent of variance accounted for, percent not accounted for, and discrepancy between the actual correlations and the reconstructed correlations. Notice in this figure that for this particular data set, 2 of the common factor methods are notably better than the other 4 methods in reproducing correlations. That is, the iterated principal factors and the maximum likelihood methods. Whereas no other method rivals the principal component method in the amount of variance accounted for in the data as shown here, over 50% right there. But this should make sense because it analyzes much more of the variance in the common factor methods as shown in the diagrams previously. And just to make a quick note here, the percent of variance accounted for, this first one, this is actually 1 minus the percent of variance accounted for. Now as we conclude, we're going to look at table 4.11, comparing the maximum likelihood method with alpha factoring method. Notice with maximum likelihood we have 39.6% of the variance accounted for. With the alpha we have 33.2, which is more than the principal factor method using SMCs as communalities, and more than the iterated principal factor method, but both are still less than the principal factor method using actual communalities. Make a note, in the maximum likelihood method with the third variable detour, we have a communality of 1 here, which is just interesting. You don't see too often, showing that factor 1 counts for all of this variable detour here. That's it for this video. We saw a comparison of many of the different kinds of factor analyses, and we compared PCA with some of the common factors, and there's pros and cons to both. Note for this data set, the Lokerta et al. 2006 data set, it seems that they chose the right factoring method for their study, particularly since accounting for the variance seems more important for their purposes than reproducing the correlations.